going to dive into statistical metrics and MDS. And Kurt and Glenn, thank you guys for setting this up really nicely. I think particularly with regard to sort of how do we deal with large data sets, as Kurt ended with, if we're getting hundreds of samples, that sort of gets overwhelming in terms of visualizing and visually comparing data sets. And it's also, again, as Kurt hinted at, it's completely non-objective in a way. In other words, there's no, you're comparing peaks together, and there's no way of saying, whether one peak fits another peak better, or whether a series of peaks fit each other better, without getting into some sort of statistical metrics. So that's where we're headed. Again, questions. I can't see the chat box right now, so if there are questions, co-hosts, please stop me, or again, just interrupt with verbal questions if you would. In terms of our course schedule, we're here, module 3, and in terms of what I hope to get out of module 3, I want you guys to be able to understand how these statistical metrics are calculated, some of the main ones that are used in detrital geochron, and what are the strengths and limitations of each. I want you to understand how metric and non-metric multi-dimensional scaling works, and how to tell the difference or understand the difference between those two, and then be able to interpret MDS plots and evaluate their quality. That's sort of the takeaways here. The outline, what we're going to be talking about, the chaos distance, the Kuiper distance, some of the similarities based on PDPs or KDEs, including similarity, mismatch and likeness, cross correlation, and then we'll see how those get applied in multidimensional scaling. So diving right out into the chaos distance, this is a statistical metric that's applied to cumulative distribution functions, actually empirical distribution functions, so abbreviated EDF, sometimes ECDF, so empirical cumulative distribution function, or sometimes CDF, right? So you'll see all of those. It basically means the distribution function based on your sample of the population, in this case of grains, that from your sandstone, for example, and it's distinguished. So we distinguish this empirical distribution function from the actual underlying cumulative distribution function. This would be the empirical distribution function is essentially the distribution function of your sample, whereas the cumulative distribution function is the distribution function of your population. Again, you're trying to sort of represent this this population distribution function by analyzing enough grains that your empirical distribution function matches that guy. So as your n goes to infinity, presumably your EDF equals your CDF. Again, even you'll see it referenced in different ways, and I'll probably default to CDF. Unfortunately, it's sort of a bad habit of mine. It's calculated basically by summing up probabilities over the age interval in question, where each discrete probability is sort of 1 over n, basically. And you just sum from 0 to 1 over that age interval. And so you wind up with sort of this step-like function, as Kurt highlighted earlier on. So we've seen this already. This should be review from earlier this morning, but I want to sort of walk through this in terms of understanding how then this feeds into calculating a Ks and Kuiper value. So if we've got two samples down here, so sample 1 and sample 2, each with 5 ages, and you can see those ages here. If we merge those two ages, we're just going to make some cumulative distribution functions for them. So sample 1 is this sort of red cumulative distribution function. And again, each time we hit one of those ages, we're just going to take a step upward. We're going to sort of cumulatively add up that probability. In this case, because we have 5 samples, our 1 over n is 0.2, and so each step is a 0.2 step up to 1, right? Same thing goes for CDF2. Because CDF1 is a function, so f of 350 is 0.2, as you can see here. F of the function of 300 or 650 is 0.4. The function of 926.5 is 0.6. These are continuous functions, and so we can compare these to other ones because we can basically subtract them from one another. Here you can see the cumulative distribution function for sample 2, and again, that's shown as a graph down here, and that graph is represented by these numbers up here, right? So these are basically the numerical equivalent of what you're seeing down here. Again, so the reason for bringing all of this up is that it feeds directly into what is the Kolmogorov-Smirnov, the KS distance, and that distance is simply the difference between CDF1 and 2. So here we've got CDF1 minus CDF2, so about 0.2 is sort of the maximum there, CDF2 minus CDF1, and so we're taking the maximum of the absolute value of CDF1 or CDF2 minus the other. And in this case, it's 0.2. So you sort of take the absolute value of one of these, or of these two columns, and you wind up with the KS distance. But it's directly related back to the difference in those cumulative probabilities. This also feeds into the Kuiper distance, because the Kuiper distance, referencing those same CDFs that we were just looking at, the Kuiper distance, that V value, is simply the maximum of CDF2 minus CDF1 plus the maximum of CDF1 minus CDF2. So we take essentially the maximum of that column, which is 0.2. We take the maximum of that column, which is 0.2, and we add them together, and that's our Kuiper test V value. So KS distance here for these two data sets would be 0.2. Kuiper V value would be 0.4. There are some limitations, particularly of the KS distance, and this has to do with its sensitivity to the extrema, right? Because the CDFs monotonically increase from 0 to 1, the variance goes to 0 as you approach either 0 or 1. So the variance in this data set necessarily goes to 0, because at some point you've got to get to either 1 at that end or 0 down at that end. And the effect of this is that if you're looking at differences in the means, the Kuiper value and the KS value tend to be sort of equally sensitive. But if you're looking at differences in the tail, so here we've got PDPs or kernel density estimates, I guess PDPs here, where the difference here is in the mean. And again, note that the KS and Kuiper are equally sensitive. Here we've got the same mean, but differences in the tails, right? So a wider distribution for this function z than for the function x. And the Kuiper distance, that V value, is more sensitive than the KS distances, the D value. So whereas the KS distance here would be 0.3, the Kuiper distance sees both of those deviations, both here and also up here, as significant, and so sort of accurately says that your distributions are more different than the KS test would indicate. And this comes directly out of some some work by Peter Vermeesch, some really excellent work, not only in his 2018 paper, but there are a couple of his papers from 2012 and 2013 particularly that lay out a lot of what we're talking about today. So those are in that literature folder in the Google Drive. I highly recommend reading those. There are some additional limitations of both the Kuiper and the chaos distance, and this has to do with the fact that they're sensitive to age proportions and distributions. So for example, we've got a bunch of relative distribution plots here on the left, so A, B, C, and D. The cumulative distributions for each of those shown over here. And what I want to draw your attention to is that between A and D, these guys share, in this case, no age mode. So, we've got the ages shown down here in the circles, and there's basically no overlap between A and D. In the case of B and D, these guys actually overlap. There are 3 ages that overlap. So you've got these two, and then this guy that are actually the same. And yet the D value for both of these is the same. And actually, if you look at the V value for both of these, that is the same as well. And so sort of inaccurately, what this is telling you is that these two distributions are equally similar. And so there are ways of fooling, so to speak, the Kuiper and chaos distances. And again, it has to do with sort of equally spaced distributions that sort of fall off of one another, right? So if you've got distributions spaced, for example, or ages spaced, for example, every 100 million years, but they're offset by 50 million years, you're going to run into the kind of problems that you're seeing here, where the chaos distance and the Kuiper distance might be giving you sort of inaccurate estimates of how different those pairs of samples are. Let me stop there before I go on. Any questions that that have popped up in the chat or that people have?
Yeah, not a single question that I saw.
Wow, I'm either being entirely incoherent or remarkably clear.
Go with the latter.
Yeah, I'll go with the latter. So a note on p-values. So often chaos distances and Kuiper distances are calculated in order to be able to run a hypothesis test. And that hypothesis is typically formulated in the form that we're looking for common derivation. So our null hypothesis is common derivation. So two samples, could they be derived from the same source? And this p-value, again, which is calculated based on the Ks or Kuiper D or V value, gives us a sense of whether or not that's accurate. And the problem is that you get a lot of false positives. So for example, a p-value, commonly interpreted, a p-value of less than 0.05 indicates that we can reject the null hypothesis of common derivation at the 95% confidence level. And the problem with that is that if you look over here, we've got a couple of examples here where all of these samples are taken from the same population. So this is from some work that Kurt and I did back in 2016. And basically what we did is we had this huge population. I forget how many millions of grain ages we sort of put into this synthetic data set. And then we drew anywhere from 50 up to 1,000 ages a couple times, and then compared those samples, right, across that range of sample sizes. And so this would be, in this case, the p-value for each of these samples. And as you can see, very quickly, we get down into sort of false positives. So these samples are coming from the same underlying distribution, the same population. So they should we should be accepting the hypothesis of common derivation. And so all of these should be above the 0.05 value. But we're getting these false positives indicating that we should be rejecting this, this hypothesis of common derivation for a lot of these samples. And the same thing goes actually for the Kuiper p-value as well. And part of the problem is that there's always a sample size at which the differences between those samples become quote unquote significant, right? So if you draw however many samples you need to, 10,000 samples, the test then says, at n equals 10,000, any deviation between these populations is significant. And there's going to be deviations between the populations just because there's natural variation. And so again, just be aware as you're implementing the KS and Kuiper tests, there is a temptation to use them in a sort of hypothesis testing sense. And I think very frequently you're going to wind up with incorrect outcomes from a hypothesis test based on the p-value. And what that means is essentially that that it's really difficult. In my experience, there's no hypothesis test that works well for detrital geochronology. And so we take a step back from that, and what we're left with is sort of relative comparison. So not can I reject this hypothesis, but simply how similar are these two samples? And the KS and Kuiper values, the D and V values definitely allow us to address that. Again, I think you're treading on very, very thin ice if you then take that next step and go to a hypothesis test. Other literature, there's some best practices laid out in this paper by Wasserstein et al. And again, that is in the literature folder in the Google Drive. There are some bullet points there, super easy read, very accessible. If you don't read the entire paper, it's at least worth looking at that to get his best practices bullet points. So that sort of takes us past metrics based on the CDF. And again, I want to pause there just because this is a natural breaking point and make sure that there aren't any questions that I've sort of glossed over. All right, if not, let's press on. And we're going to be looking at metrics then based on PDPs and KDEs. And our first
quick question.
Yeah, go ahead, Isaac.
Just for clarification, you said that the KS and the Kuiper tests, for our purposes in geoscience, usually aren't the best for hypothesis testing, but at least a quantitative method for comparison of samples. Is that what you're getting at?
Yeah, exactly. So good for relative comparisons, bad for hypothesis testing. Other questions? All right. So our first sort of metric based on KDEs or PDPs is called similarity. It's also known sort of in the statistical world as the Bhattacharya distance, sort of developed by an Indian statistician. I forget his first name, but Bhattacharya back in the 40s. It was introduced to geochronology by Gerels in 2000 in one of his seminal papers on geochronology, and it's based on the observation that, as we've mentioned before, these KDEs or PDPs, we think of them in terms of sort of continuous functions, but in fact they're discrete, or at least they can be discretized into points along a continuous function, right? And so that gives us the possibility then of taking each of these points, so a point here, and multiplying it by that same the point at the same age in function g, and again taking a point here in function f and multiplying it by that same point in function g. And so what that gives us is, we go through these two functions, multiply these guys together for all x. We multiply f of x times g of x, and we take the square root of that. We sum over that distance. So what I've got down here is just these two functions overlaid. So g and x sort of laid on top of each other. And then the purple overlay here is just those two multiplied together. And then we would simply sum over this distance, right? Or that age interval. In this case, our similarity is 0.84. And I should say that this varies from 0 being totally dissimilar to 1 being totally similar. So 0 is absolutely no similarity. 1 is a sort of perfect match. And by comparison, the KS and Kuiper tests are going to go from 1, which is totally dissimilar, to 0, which is identical. So they're sort of inverses of one another. Again, minor point, but don't get too hung up on that. So again, similarity, pretty straightforward, hopefully. Mismatch and likeness. Again, another fairly common metric that's used in geochronology. Again, we have those same two functions, f and g, and in this case, we're simply going to subtract them. So it would be the absolute value of f of x minus g of x, and all of that divided by 2, so that you get so it sums to 1. Down here, you can see, in this case, we've got f and g. The purple here is the difference between them, and then we would sum over this distance. Like the KS and Kuiper tests, this guy goes from 1, which is totally dissimilar, to 0, which is totally similar, and that's for mismatch. So yeah, ranges from 1, which is no overlap, to 0, which is identical. And that was modified by Sadkowski et al. In 2013 to a metric based on that, which they called likeness. And that's simply the complement of mismatch. So likeness for f and g is 1 minus mismatch for f and g. And the idea was to make it more similar to, for example, similarity or the cross correlation coefficient, where you go from 0, which is no overlap, to 1, which is identical. In terms of the calculation, these guys are basically the same. Again, the only difference between likeness and mismatch is this equation here, where likeness is the complement of mismatch. So L equals 1 minus M. In this case, if we, for the two data sets that we've been looking at, the likeness value is 0.6. Recall that for this data set, our similarity was 0.84, and then V was 0.4, and D was 0.2. And so again, the same data is giving us slightly different metrics or slightly different values, suggesting that we can't really compare a 0.6 likeness for these two sample sets to a 0.6 similarity for another 2 sample sets. If you're going to compare your data, it has to be essentially entirely internally consistent. And quite honestly, it doesn't matter a whole lot which of these you choose. Some of them are slightly more sensitive to others. Some of them have slight advantages over the others. But being internally consistent and realizing that they're all sort of relative comparisons is really one of the first steps to sort of making sense of these comparison metrics. All right, so likeness and mismatch. And then sort of going on to cross correlation. This is a really straightforward, you guys are all familiar with this. This is essentially the Pearson correlation coefficient. It's used all over the place in signal processing and template matching and image matching, geophysics. I mean, everybody uses it, right? And so basically what we're doing is we're taking those discretized PDPs and we're plotting them for the same age. So, at age 0, we've got a point there. At age 500, we've got a point there for both PDPs. For age 1000, we've got a point there for both PDPs. So plotting the same ages as cross plots here, and just taking, again, the Pearson coefficient of determination between those. And you can see the equation there. I'm not going to belabor the point of how you calculate that. One of the really nice things about this is that it's sensitive to both the location and also the distribution of modes, and actually also the shape of the distribution of modes. It does, so we square it. The squared function ensures that it ranges between 0, which is no overlap, so totally dissimilar, to 1, which is identical. And yeah, I think that's about all I'm going to say about that. For that same sample set that we were looking at previously, recall our likeness was 0.6, our similarity was 0.84, V and D were 0.4 and 0.2. Our cross correlation coefficient for those guys is about 0.24. So the cross correlation coefficient is telling us that these guys are actually fairly dissimilar, that only 24% of the variance in PDP-1 can be explained by the variance in PDP-2. And it is fairly sensitive in my experience. Unfortunately, all of the metrics based on PDPs or KDEs have some limitations, and those have to do with the discretization, for example. So if we've got 2 samples, these are in both of these, the purple, or sorry, the dark blue and the light blue are the same data sets, just discretized differently. So in the upper one here, we're looking at a probability point every 1 million years, and that gives us a cross correlation coefficient of 0.41. If we take that same data and we discretize it as at 100 million years, so a probability data point every 100 million years, we wind up with a different cross correlation coefficient, and actually a higher one. So it's suggesting that if you discretize this differently, they appear more similar than if you sort of look at the details. So be aware that how you discretize these can be a factor in your cross correlation coefficient. And so again, treating your data in a consistent way is essential to coming up with sort of accurate interpretations. In my experience, if you're looking at fairly broad age ranges, so age ranges on the order of probably greater than, let's say, 500 million years, so you're going from 0 to 500 or 500 to 1,000. Anything bigger than that, a million-year discretization is probably fine. If you're looking at age ranges less than about 500 million years, you might want to consider a finer age step. But again, play around with that, I guess, is part of the point.
Joel, can you take a chat question real quick from Isaac about does what you're talking about have implications for samples with large numbers of analyses?
It doesn't really. So the number of analyses gets to how well you're sampling the underlying population. So how close your sample PDP matches some theoretical population PDP. but once you've taken those analyses and you've turned, your either 10 samples, your 10 grains or your 1,000 grains into PDPs, you can discretize those PDPs at the same resolution. So for example, you could take a PDP with 1,000 grains and discretize it at 1 million year intervals. You could take a PDP with 10 grains and discretize it at that same interval, and then you could directly compare them. Does that sort of answer the question? Hopefully.
Yep.
All right, cool. The other thing that becomes an issue is that that these guys depend on the age range that you're looking at. And so again, we've got those same sample sets up at the top here and down here. Note that you're looking at very different age ranges, but the same X interval. So discretized at 1 million year intervals, but going either from 0 to 4,000 or 0 to 1,000 million years. And your cross correlation coefficient actually changes because of that. So if you only look at this younger interval, again, the cross correlation coefficient indicates that those are more closely matched than if you look at the entire interval, which is, again, it's both a strength and a failure of the method, right? So you can say, well, given that, I know that this is sort of where the difference is, and what does that tell me about the sediment sources for my basin? And it might tell you something pretty interesting. But if you're not being careful about how you're reporting this data, it can be quite misleading. And then finally, sort of driving home that same point, that for cross correlation particularly, even zeros matter, right? So in this upper one, again, we're going from 0 to 4,000, but notice that there's basically no data out here beyond about 3,000. So let's just chop that off, right? And now we're going from 0 to 3,000, but note that this has changed our cross correlation coefficient. And this gets back to how this thing is calculated. Essentially, from 3,000 to 4,000 million years, you got a bunch of zeros just sitting down here, and it is influencing how well that line essentially fits that data, right? So you're artificially weighting the cross correlation coefficient by sort of forcing 1,000 data points that correlate perfectly. So age ranges can be a huge issue. So discretization and age ranges affect all these guys, and actually affect for the CDFs. If you make a CDF based on summation of a PDP or a KDE, then that's going to similarly, those same considerations are going to affect your D and V values as well. All right, again, I want to pause for just a minute and make sure that people are still with me.
I just had a quick question. In the Vermeesh 2013 paper, he defines delta as the dissimilarity. Is there a reason that people use the dissimilarity instead of the similarity, or are they kind of, interchangeable in a sense, if that makes any sense?
Yeah, so yeah, technically that is accurate. I mean, dissimilarity is a more is a technically more accurate way of describing these metrics than similarity, because you're looking at the deviation one from the other. But I mean, bear in mind that dissimilarity is simply the complement of similarity. So to define one is to define the other. And as you can tell, I use the terms a little bit loosely.
All right, thank you.
Yep. All right. So I'm going to press on to multidimensional scaling. And multidimensional scaling, one of the key things to understand is that it is merely a way of visualizing a dissimilarity matrix, right? So once you've done all the work and calculated whatever dissimilarity metric you want to for all of your samples, you get a matrix that sort of, it's a square matrix, and it shows the dissimilarity between each pair of samples. Multidimensional scaling simply takes that matrix and represents it in Cartesian space. It provides basically no other information. And in fact, you often sort of lose a little bit of resolution when you do this, because you're actually sort of forcing the data into a two-dimensional or three-dimensional space. But what it does is it allows us to sort of visually see that dissimilarity matrix in Cartesian space, and hopefully be able to pick out relationships based on that visual representation of a table, essentially. So it converts dissimilarity to distance. So we're talking about sort of the converting that matrix, a tabular matrix, into sort of Cartesian space. And it does this by iterative rearrangement of the samples in Cartesian space, where in this case, P of I and J is just the dissimilarity between samples I and J. D hat is the distance between samples I and J in Cartesian space. And it's a transformation, so the F of P. And that D hat is referred to as disparity, or approximated distance, to distinguish it from the final plotted distance. And that the final plotted distance we're going to refer to as D of I and J. So D hat is the disparity, D is the final distance in our plot. And so what we're trying to do is minimize the difference between our disparity, right, that calculated distance between I and J based on this function, and D, which is the final sort of how our plot does in representing that. There are a couple ways to do this. There's non-metric, i.e. qualitative or ordinal, and then there's metric, MDS. And we'll talk a little bit about each of those in turn. Before we get to some of the details, I want to try to walk through an example to give you an intuitive sense of what MDS is doing. And the best example that I've come across is this example from a textbook by Borg and Gronin from '97. And what they have in their textbook is a table of the distances between 10 cities in Europe. So we've got 10 cities labeled 1 through 10, and their relative distance. This would be the distance from city 1 to 2, from city 1 to 3. And as you can see, as I described, this is a square matrix. It's just a table. And it's pretty difficult, at least for me, to get an idea of how a map of this would be laid out. Like how similar is 7 to, or how close is 7 to 6, right? The number is there, you could figure it out, but it's non-intuitive because we are visual creatures. So MDS proceeds by taking essentially the biggest distance here. So that would be between city 2 and 3, and you simply plot those guys, right? So that's the distance between 2 and 3. And then you take the next biggest distance and you start to triangulate those intermediate distances. So for example, between 9 and 2 and 3, we've got those distances. And so we can start to put together, there's a radius of 714 kilometers from 3. We'll draw that circle, a radius of 787 from 2. So we wind up with 2 points, obviously. So 9 and 9 prime. We have to make a decision. Which one are we gonna select? And in fact, it doesn't matter, because from this point on, it's just a reflection, and reflections in MDS space are fine. Eventually, we get all of our points plotted, right? And and they're constrained by multiple pairs. So for example, 9 here is constrained, its location is constrained by its relationship to every other point on the map, right? And so there's very few, it's actually, you can tie it down pretty directly because it's got all of these interrelationships, right? So that's just for 9. And the same thing goes for each of these other points. You know, if I drew all of the interconnections here, it would just be a massive scribble. You wouldn't be able to see anything. Because they're so interconnected, because it's representing all of the data in this table, which is a lot of data in a Cartesian space. And again, we can rotate this, we can reflect it, we can scale it, because MDS units are not real units, essentially. So this is what we wound up with. You know, this is sort of, we took our our default result. So 2 is up there, 3 is down there, 9 and 10. And that's what we've got here. So 2, 3, 9, and 10. We've now labeled those with our city names. We can reflect that. That's fine. Remember, we could have chosen 9 prime instead of 9. And it turns out that 9 prime was probably the one to choose. We can rotate that, right? So now we've got our, you know, in this case, we've put the ordinal directions on here. We can rotate those ordinal directions to north. Again, all good. And then that matches essentially a map of Europe pretty accurately. So rotate, reflect, scale, it's all good. Just, you know, you can't move one of these plots or one of these points relative to the other ones. And you can't sort of arbitrarily scale part of the image relative to the rest of it, because then you're breaking those relationships in distance. So that's metric MDS. That's sort of how the metric MDS proceeds. Non-metric MDS basically assumes that the degree of separation is not as important as the relative ranking. So we're going to take those same distances that we had, and the smallest distance has a rank of 1. So we're just ordering them from smallest to largest, right? From the closest distance to the furthest distance. So 1, 2, 3, 4, etc. And then we proceed, you know, on the same basis as metric MDS, but it narrows down zones of occupation. So we know that this sample is closer than another sample, but further than a third sample. And so we wind up with this zone of occupation. So again, if we're looking at one sample, we know that another sample up here must be closer than a third sample, but must be further than, you know, that sample. And so that sample must fall somewhere in that zone relative to that guy. And again, because this matrix is so data rich, even using sort of these zones of occupation, it narrows it down to a pretty reasonable reproduction of that European map, as you'll see on the next slide here. So comparison of metric and non-metric MDS, they're usually really similar. So in this case, the metric MDS are the solid points, the non-metric MDS are the open points, and you can see they fall basically right on top of one another. And again, this is straight out of that textbook from 97. All right, so basics of MDS. Any questions before I go on?
There's a question in the chat. So if you choose, say, going back to your 9 prime versus 9 slide, if you choose 9 prime, then do you choose the prime for all of the others, so X prime for all of the other triangulations?
Yeah, so that decision would have cascading effects, because then everything, you know, all of these other ones that are relative to 9, you know, you would have to relate them to that point rather than that point. So that decision would have, again, cascading effects in how your map would look. But again, it would simply be the difference between these two guys, right? It would be that reflection. And so it doesn't really matter. Other questions?
No more in the chat.
All right, great. So I'm going to go through a couple of examples here to give you guys a sense of how we assess the quality of multidimensional scaling problems. And so I've taken a sort of synthetic data set made up of 10 sources here. This actually, I think this comes from your paper, doesn't it, Kurt? The DZ mix paper?
Yeah, it looks familiar.
Yeah. So these 10 sources were mixed in various proportions into this mixed sample. Doesn't really matter. All that you need to know is that we've got 11 samples here that we're going to try to show in MDS space. In this case, the metric that we're going to try to do this is the D value. And so we wind up with this guy. And so all of these guys are related to the MDS plot in different to different degrees. Typically, when you show an MDS plot, you also want to show a shepherd plot, which is this guy, and you want to report the stress. So the shepherd plot basically shows the dissimilarity, which is essentially rank in this case, and the disparity, and that's shown by the red dots and connected lines here. On that same plot, you can show dissimilarity again on the x-axis and distance, so that final distance, right? So we're showing d hat as the red lines or the red dots, and d as the blue dots or the blue data points. And ideally, these guys would fall right on top of one another, and that would give us a stress of 0. And clearly they're not, right? So there are some points here that fall off of your expected or your predicted disparity. And so there is some stress. It's not a particularly high stress. That's a fairly good value. 0.1 is probably acceptable. 0.2 is pretty good. Above 0.2, you're sort of having issues. But if people are showing, if you're going to show an MDS plot, you need to present sort of the additional data that tells your reader or your audience how well your MDS plot matches your expected transformation. And I'll show you why in just a minute. So we can do the metric, we can do a metric transformation based on that same data set, and it looks similar. It's not going to be exactly the same. The shepherd plot in this case, we've got, again, the disparities shown as the red dots and connecting lines. In this case, your dissimilarities are being transformed to disparities, basically a one-to-one transformation. And again, you want your distances to fall right along that one-to-one line, ideally. They don't fall along that one-to-one line. They deviate from it a little bit. And so your stress is a little bit higher. So getting up towards 0.2, not quite as good. And notice that there's some differences between these two plots, right? So for example, looking for source 6 and source 3. So this distance here is quite a bit different from this distance here. But if we transform that, so going through that reflection exercise, I'm going to reflect that, and notice that there are, regardless, despite the fact that there are some differences, there are a lot of similarities. So source 5 up here, more or less on its own. Source 1 out here, more or less on its own. 6 and 3, although the distance between them is slightly different between these two plots, they both plot down in the bottom left, and they are sort of connected, or they're most closely connected to source 10 and source 9. So maybe not as good an example or overlap as that example from the textbook, but there's definitely some similarities between this non-metric MDS and the metric MDS, again, based on that KSD value for this data set. We can look at some other metric MDS values. So in this case, we're looking at the KSD value based on a squared stress. And I'm not going to get into what exactly squared stress is. It's simply a different method, a different calculation of, or a different way of calculating the misfit between the distances and the disparities. There's our shepherd plot for this guy, stress of 0.17, 0.18. Same data set, same stress, Kuiper v-value gives you a stress of 0.23. And again, notice that there's some similarities here and some differences. Where you start to wind up, or where you get into problems is, over here, right? So in this case, we've got a cross correlation. Again, same metric, same data set. Our stress is 0.41, and the MDS plot looks quite a bit different. But imagine if I only showed this MDS plot down here and didn't provide any of this additional context. I might be able to convince you that this is a perfectly fine representation of the dissimilarity relationships between these samples, because I haven't fully reported the quality assessment of that data. So be aware of sort of how you're reporting your data, how other people are reporting the data, and whether or not that the correlation metrics and the MDS plots are providing a good representation of the dissimilarities between your samples. This would be an example where you might have calculated that dissimilarity matrix based on the cross correlation coefficient, and then you have that data, but then you're trying to represent it in Cartesian space, and you're actually losing information. So this is a sort of losing information proposition. You're doing a bad job of representing that dissimilarity matrix in Cartesian space. And so this actually obfuscates. It doesn't provide clarity on the relationship between these samples. It actually loses clarity, right? You're sort of obfuscating the relationship between those samples because your transformation is poor. All right, so that's the end of the show here. And I want to, again, ask if there are questions, but pretty quickly we're going to transition to working through some of these examples. So I think I went a little bit long there.
You did get two good questions in the chat. The first from Mark: does having a small group of samples with very different distributions have an effect on the total stress? And then from Isaac: do you use the goodness of fit rule of thumb for stress that Vermeesh proposed in 2000?
Yeah, it's a good question. Yeah, both good questions. So yes, the stress is a function of the number of samples that you're going to have. And so, again, in addition to the stress, and in addition to just reporting that stress value, I think it's useful to report to show these shepherd plots because of that, right? So you can have very few samples which will correlate to a low stress value, despite the fact that your distances and disparities might be pretty bad. They might not match very well. So yes, the number of samples is going to affect the stress. In terms of the rule of thumb that Vermeesh gives, I forget what he gives, honestly. What I quoted as a stress of 0.1 being good and 0.2 being acceptable is something that I learned from a statistics textbook. I don't know when, ages ago.
So Joel, I pulled it up. It actually comes from the seminal work of the Kruskal method, where a lot of this derives from. So Vermeesh is quoting that, and he basically lands where you land. Poor would be like a 0.2, fair would be 0.1, good would be 0.05, excellent 0.025, and obviously perfect is 0. It's his table.
I don't know if I've ever gotten stresses that low, particularly with large data sets. So yeah, I guess I do fundamentally agree with that sort of rule of thumb.